Why are we allowed to do that?
Because the E and L cancel out.
Yeah. Remember, the exponential with a base of e is the inverse of a logarithm with a base of e. So this does equal 2. We're not just doing some kind of a trick here. It does actually equal 2. But notice why we did that. Okay? Here, we have e to the ln of 2. Now it's to the x power because we had 2 to the x power. Alright? If you remember yesterday, the derivative of e to the x was e to the x, but we never looked at any other bases. Okay, and I don't know if any of you thought about this as you were doing it, but what about other bases? Obviously there are other exponentials that don't have a base of e. How do we handle those? Well, here what we did is we substituted e to the ln of x in for 2, and when we simplify, you multiply the exponent, so it's e to the x times the natural log of 2. Now we can take the derivative because we have an e to the x. Okay? The derivative of e to the x is e to the x, or e to something is e to that something. But since there's an expression up here, we have to then multiply using the chain rule. Okay, so we multiply by the derivative of this exponent, which is just the natural log of 2. Okay, that's because natural log of 2 is a constant, and a constant times x to the first, you just get the constant then when you take the derivative. Alright, so simplifying this, I substituted back in the 2. Okay, I noticed, hey, this is e to the natural log of 2. That equals 2, but that's to the x power, so I put the 2 to the x back in there. Okay? So you can see here, the second part is saying, show that if y equals b to the x, where b is positive but not 1, then the derivative is b to the x times the natural log of that b. Well, here it worked. We have 2 to the x times the natural log of 2. So they want us to then use the process that we used on part A to prove that it works no matter what the base is. Okay? So let's think this through. Instead of substituting e to the natural log of 2 in for 2, I'm going to substitute e to the natural log of b in for b. Okay? Again, the e and the exponential and the natural log are inverses, so that does just equal b, so that's b to the x. I simplify that down, e to the x times the natural log of b. Okay. So now I take the derivative, the derivative of e to something is just e to that something. Then using the chain rule, what's the derivative of x times the natural log of b?
Natural log of b.
The natural log of b. Okay? So that's the natural log of b. Alright? Now we'll do that back substitution again. Okay? We have the natural log of b times e to the natural log of b to the x power. And that just equals b. So the natural log of b times b to the x power. So that rule works for everything. Any base. Okay? In fact, it even works for e to the x if you think about it. Okay? The derivative would be e to the x times the natural, let's write h, times the natural log of e. Well, what's the natural log of e? 1. Okay, it's 1. So that's why equals, it even works when the base is e. Okay? Now let's go back here for a moment. This might have been a question that you asked, or you were thinking about, is what about other bases other than e? Right, so here's the rule that we just looked at. If y is b to the x, then the dy dx is the natural log of b times b to the x. So this is going a little bit beyond IB, but I think it was a valid question to ask. So let's just run through a couple of these. What if y is 5 to the x? What would the derivative be? Good, the natural log of 5 times 5 to the x. Okay? Natural log of 5 times 5 to the x. Okay. What about 10 to the x? Yeah, natural log of 10 times 10 to the x. Okay. What about y equals negative 10 to the x? Anyone? Wouldn't it equal the natural log of negative 10 times negative 10 to the x? What is the natural log of negative 10 though?
Is it undefined?
It is undefined. If you remember, your natural log function looks like this, right? Because e to any power is never going to give you a negative value, right? Or, I'm sorry, negative 10 to a power will never give you a no, that was right. E to any power is never going to give you negative 10. Sorry. So, this is undefined. Alright, so our whole derivative is undefined. Okay? Alright, so, and the reason for that, this is why they included back here where b is greater than 0 and doesn't equal 1. Okay? Because if it's 1, it's just 1 to a power and that equals 1. But b has to be greater than 0. Okay? So, there we have it. Okay? Alright. Any questions? Yes.
May I go to the restroom?
Anything else? Alright. So, what I want to look at today is the derivatives of log functions. Okay, logarithmic functions. We are going to isolate our focus on the natural log. The reason why we only need a natural log one, I'll show you here, is if you remember, if we had a log, let's say we had a log base 10 of x squared. Do you guys remember your change of base formula? You can change the base of a logarithm by writing this as the natural log of that x squared over the natural log of the base you were using. Okay? So we actually don't need to bother with any other rules other than just a rule for if we have the natural log of x. Okay? Because if we have a different base, we can use the change of base formula to get it to be the natural log. Alright? And in fact, this here would just be a constant. Alright? So we wouldn't even have to use the quotient rule. It would just be a constant. Anyways, you'll notice here, if y equals the natural log of x, then the derivative is 1 over x. So this is kind of nice. There's no real formula or anything that you've got to plug it into. You just have to memorize it. Derivative of natural log of x is 1 over x. Now, as we saw with the exponential functions, where this gets a little more challenging is when you have something where you have to use the chain rule. Okay? We're not just taking the natural log of x, it's something like the natural log of the square root of whatever. Okay? So, what we have in this case is if we're taking the natural log of a function, it's going to end up equaling f prime of x over the f of x. You might say, well, how in the world did they come up with that? Well, let's look at it. Okay? If I have the natural log of f of x, I have to use the chain rule, so it's the derivative of the outer function, which is 1 over whatever you're taking the natural log of. So it's 1 over f of x times the derivative of the inner function. The inner function here is f of x. So we're going to multiply by f prime of x. That's how we get here. Okay? So I know it may have been a jump to get there without seeing that middle step, but hopefully that clarifies it a little bit for you. All right. So let's see a little bit of this in action here. Let's start with y equals the natural log of 1 minus 3x. Okay, the natural log of 1 minus 3x. Here we're going to have to use our chain rule. Okay, so the outer function is the natural log, so I would have 1 over what I'm taking the natural log of. So it would be 1 over a 1 minus 3x. Here comes the chain rule. We're then going to multiply that by the derivative of the inner function, which is what? Negative 3. Okay? Negative 3 is the derivative of 1 minus 3x. So now we put that together, and we get a negative 3 over 1 minus 3x. Okay? So, it's a simple chain rule problem. Just got to be careful when you're doing it. Probably the most common mistake people will make is they want to put this derivative of the inner function down in the denominator with it. Okay? Don't fall into that trap. You're multiplying, you're putting 1 over the function, then you multiply by the derivative of the inside. Okay? Now, what do you see about this one? What are we going to have to do to find the derivative of this function?
Can we get the exponent Like, isn't that like a little like,
You could, I mean, technically you could rewrite this as the natural log of x to the x cubed power. I wouldn't recommend it, but it does work. Okay? Does work. What else could we do instead?
Is the u, this is the u v, u prime v plus u v prime is multiplication doesn't work.
Exactly, yes, this is multiplication, so we're gonna use the product rule. Okay? U would be our x cubed, v is the natural log of x, so u prime would be a 3x squared, and v prime would equal, what's the natural log of x? It's a derivative? Derivative of natural log of x?
1 over x.
1 over x, there we go, 1 over x. So now we can use our product rule for dy dx. U prime times v plus u times v prime. And that does simplify a little bit. I wouldn't simplify the first part at all. But this does simplify down to an x squared. Okay?
In this study,
How picky are they going to be on the exam, do you think, with simplifying? It's like, I don't know.
I think if you kind of follow the rules that we've established in class, you'll be fine. Like for example, if you wanted to on this one, this is fine, and I don't think IB's gonna have a problem with this at all. Okay, if you really want to, if you see, hey, there's an x squared in common, you could make that 3 times the natural log of x plus 1 times the x squared. Okay? Is that helpful? Maybe in some cases, but this is certainly fine.
So if you come to a problem like where you're not sure, it looks like it's big, but then like I think on the test I did this, I simplified wrong. Like I took something out that wasn't technically like allowed.
Mm-hmm.
So is it better to just stop if it's like long, or to try and because I'm really bad at knowing when to simplify and when it's not allowed. When you're allowed.
I think the basic rule of thumb
I
is
understand
kind of what
that.
we've been mentioning. No negative exponents. Avoid the complex fractions, except we had the one case yesterday where we had like a 2 over e squared plus something, and then that was to the 3/2 power. Trying to get that to not have a fraction inside there is a pain, so don't worry about that. But yeah, no negative exponents, simplify complex fractions, distribute,
Yeah.
okay? If it's a simple matter of just foiling, it's not a trinomial times a trinomial or something like that, you might consider going ahead and simplifying. The cases where we used the product rule with the chain rule, or the quotient rule with the chain rule, and then you had that GCF that you could pull out, I would definitely do that. Okay, so I think what we're doing in class, if you just follow that model, you'll be fine with the IB. And two, we're gonna do some more practice with exactly IB questions, and we'll look at those mark schemes. So we'll see kind of cases where maybe they simplify a little more, or maybe they don't bother simplifying as much as well. So. All right, now, Charlie mentioned the rules for logarithms, okay? And that is one thing I want to talk about here, because if you use those, it really makes a lot of these problems much, much simpler. Okay? So let's take a moment here and recall what those were. We already said if you have a number outside the logarithm, you can bring it in as an exponent. Or if you have an exponent in your logarithm, you can bring it out in front. So if I have the log of x squared, I could write that as 2 times the log of x. Okay? Yeah, Lord? Jay?
You can change the base of a log.
We can change the base of a log, like we saw at the beginning there. If you have a log with a base of 10 or a base of 2 or something like that, our change of base formula, changing it to natural logs, you really have to do in order to be able to find the derivative. Okay? What if we had the log of two things multiplied together, like the log of a times b? What could we do with that?
Isn't it ln a plus the
There you go, the natural log of a plus the natural log of b. If you have multiplication inside the log, you can split it into two that are added together.
It's division and subtraction.
Exactly. If it's division, it's subtraction. Okay? So here you have these. The natural log of a times b is the natural log of a plus the natural log of b. The natural log of a divided by b is the natural log of a minus the natural log of b. And then here, if we have the natural log of a to some power n, we can write that as n times the natural log of a. Now, can you do these just using the chain rule, and then when you find the derivative of the inside, like for this one, use the product rule? Absolutely, you can. Is that the most efficient way? No, as we'll see. Okay? Here, you'd have to use the quotient rule, and then when you were finding the derivative of the denominator, you'd have to use the product rule. So we definitely would like to find an easier way of solving that one. Okay? So let's look at how we could use these rules. First of all, on the left here, we have the natural log of x times e to the negative x. So let's think about this one. Notice I'm not doing the derivative yet, I'm just simplifying the function itself. So I could write this as the natural log of
x plus the natural log of e to the negative x, which will just be ln x plus the negative x. I mean minus the x. Because if you take the natural log of e, it's just going to be negative x.
okay, but it wouldn't be plus that. We would take that negative x.
It will be minus. So ln x minus the x.
Well, it would be the minus x times the natural log of e. When you have an exponent right here, it's that exponent times
Yeah, but
the log of
isn't
the
it
base.
Natural log of e just 1. So
It actually is. Okay? That does end up equaling 1. Okay? So we have the natural log of x. Maybe I was misunderstanding what you were saying. Okay? And once we pull out that negative x, the exponent negative x, natural log of e is just 1. Okay? So the function we're really finding the derivative of is this. Okay? Well, that's pretty simple, right? What's the natural log? What's the derivative of the natural log of x?
1 over x.
1 over x.
Oh.
What's the derivative of a minus x?
Minus 1 over
Minus 1. And that's it. Now, would you get the same answer if you did the chain rule with the product rule? With the chain rule a second time?
Yes.
Yes. You would get there eventually, but you'd have a whole lot of simplifying to do. Okay? Because here you'd have to do 1 over x e to the negative x times the derivative of this, which you'd have to use the product rule for, so it'd be 1 times e to the negative x, there's the u prime v, plus u times the v prime, which would be e to the negative x times a negative 1. Okay? And I don't know about you, but it's kind of a pain. Although, when you distribute here, I have e to the negative x over x e to the negative x plus x times e to the negative x. I'm going to bring that minus 1 out here in front, so it'll be minus, and that's over x times e to the negative x. So what does this equal? So out of e's and negative x's there, but what is this all?
1 over x minus
Minus 1. So we got there, and I was able to do it pretty fast, but that's a pain, okay? It's a whole lot easier to simplify first and take the derivative of that simple function, okay? So, we don't want to mess with that if we don't have to. Alright, so how about this second one? How would we simplify the natural log of x squared over x plus 2 times x minus 3?
The natural log of x to the second power minus the natural log of the denominator.
Okay, minus the natural log of the denominator. Okay, so could we simplify that a little more, Alex?
Can you separate this x plus 2 times x minus 3 to make the natural log of x plus 2 and the natural log plus the natural log of x minus 3?
Okay, that'll work. One thing to be careful with when you do a denominator that has multiple parts is if you're going to write this as natural log of x plus 2 plus the natural log of x minus 3, make sure that you distribute that negative to both parts. Okay? You were dividing by both parts, right? So you'd have to make sure you distribute the negative to both parts. What I prefer to do is just to think of it in terms of, right off the bat, I'm dividing by both of these, so it's going to be minus that minus the natural log of x minus 3. Right? Okay. Because I was dividing by both of these factors. How could I simplify the natural log of x squared? Am I?
2 natural log of x.
Yeah. And you see how simple this gets once you simplify the function itself. Two times the natural log of x. What's the derivative of that?
2 over x.
2 over x. Natural log of x is 1 over x, so times 2. Minus, what's the derivative of the natural log of x plus 2?
1 over x plus
1 over x plus 2. Now, be careful because the chain rule applies here.
2 times the 1.
Times the 1. So the nice thing is the derivative is just 1 in the inside. Okay? And then likewise the last one.
1 over x minus 3.
Good. 1 over x minus 3. The derivative of the inside is 1, so that's it.
Would you simplify? Like, would you?
Like get a common denominator?
Yeah.
No, I wouldn't mess with that. Here's the thing, we simplify if it'll make it easier to do things like in the future. if I wanted to take the derivative of this again, as we'll see later, we'll do second derivatives and third derivatives, which is actually the last section of this chapter, but I'm gonna put that with chapter 16 instead. But in this case, actually keeping it separated kind of helps us find the second derivative a little easier, I think. If we were doing something like finding where this equaled 0, then maybe I would go ahead and get a common denominator and whatnot. But if we're just asked to find the derivative, this is perfectly fine right here. Okay. Alright. So, are there any questions? Relatively straightforward. It's just a matter of practicing it. Okay. There are only 2 on the worksheet for tomorrow that have logs in them, and I did that just because I have some from the book that we haven't done yet. You can use to practice some of those. Again, here they specifically say use the laws for logarithms to help you. Okay, don't try to just do them as is. Simplify it. And that'll make life a whole lot easier for you, okay? And then of course the last 2 are more of the critical thinking type of questions where you've got to, do some problem solving and make sure that you really understand what's going on, okay? All right. So I think that's it for today.